recording? Yeah. Right. So in today's lesson, first we introduce working in 3 dimensions. Right. Everything up to now has been on the plane, so in 2 dimensions. But in the real world, things are in 3 dimensions. And so we got to add a component to our vectors. Before we talk about it in terms of the vectors, though, we have to just describe how is it that we graph things in 3 dimensions. So there's a little bit of 11.1, which is about that, but most of 11.1 I cut out just because I consolidated these to get us farther. It's not much lost. But in 3 dimensions, you're going to have an x-axis, a y-axis, and a z-axis. I mean, if you could imagine, an x and a y-axis in the plane like that. If you're the third axis has got to be perpendicular to that, right? So if x and y are flat with the board, then the z-axis would be coming straight out of the board. It would be perpendicular to both the x-axis and the y-axis. Now, that's not exactly what you see there, because that is not the way we usually draw these axes. Let me take this off. So usually the y-axis is drawn flat with the board, and the z-axis is drawn flat with the board. So that you can see that this here is a 90-degree angle. Let me write that in red. It's an angle. That's a 90-degree angle. And then it's the x-axis that we're trying to show is coming out of the board. But we're doing it by trying to use the perspective, like if you were drawing train tracks, right? If you were drawing train tracks, you would draw them something like that. Now, these lines are getting closer together, but are the train tracks really getting closer together? No. The ties look like they're getting closer together, but are they really getting closer together? No. Well, that's the same thing here. We're just trying to show this is kind of a depth to it. This x is coming out of the board, and it is also perpendicular, right? It's got to be perpendicular to that, and it's got to be perpendicular to that. Those are all right angles. And this thing here is just trying to show those 3. Now, usually the way I draw it up here is like this, and it's not 100% consistent with everything they do in the book. Sometimes in the book, that is exactly what I'm about to draw. Okay, you're going to draw the z-axis, you're going to draw the y-axis, right? That's z and that's y. And then you draw the x-axis at an angle like this. So that's coming out of the board, right? It's the positive x-axis is coming out of the board. Negative x is going into the board, right? The positive y-axis is going to the right, right? Negative would be to the left. Positive z is going up, and negative is going down. And that is exactly like they've drawn that right there. But yeah. So if you're going to plot any point in space, it's going to have an x and a y and a z coordinate. And so, the x is going to tell you how much you want to go this direction, right? Positive will be here, negative will be there. The y will tell you how much to go left and right. And the z will tell you how much to go above or below. But it's all about trying to picture it. And if you have a hard time seeing some of these things in 3D that are really written on a 2D surface, right, then it'll be a little harder. The book, because they've got all the advantages of the graphics and different colors and things like that, I think their graphs tend to look a little easier to see what's going on. So this is in their example 1, where they're graphing 3 points, right? And the points are here, 2, negative 3, 3, negative 2, 2, 6, 2, 1, 4, 0, 2, 2, negative 3. And you can see the way that they've done it. Now, first of all, their axis is not like that. they've tipped the axis now where this is not a straight line going across. It's actually going down. Now this is still coming out of the board somewhat. This one is still flat, but it's not exactly the same. Usually when I draw them, I don't try to draw them like that. I try to draw them like I did on the last. Like I would go like this. Okay, X, Y, Z, right? Now, when you're trying to graph the point, let's say -262. So in the X direction, since the coordinates are X, Y, Z, right, that means on the X-axis, you're going to go back 2. And again, I'm drawing these like railroad, the ties on a railroad track to show that everything's parallel and it's going into the board. And now it's 6 in the Y direction, which would make it 1, 2, 3, 4, 5, 6. So if I just found where is that would be about right there. Okay, that's taking care of the X and the Y. Now the Z is +2. So then we have to go, if you can picture that we are in a flat surface, we're in the behind the Y-axis here. You're going to go 2 above. Now, how do you picture 2 above? I usually just try to picture what would 2 above have been right there if I was at the origin. It would have been about that distance there. So I'd come over here and say, okay, it's about right there. Now, they've done about the same thing, right? They've gone X is -2, Y is 6. That brought them to that point in the XY plane, and then they went about 2 above and drew a point. What's that? Huh? I'm not quite seeing it. I mean, it's probably just because of the way they've tilted theirs down like this. I mean, I'm not going to ask you to graph points because it's just too confusing to look at it and just asking for trouble. But you do have to understand, we're working in 3 dimensions now, and there is some perspective to it. I would say that one of the things that people have trouble with when they go to calculus is that you do have to do some 3-dimensional kind of thinking. It's not everything in the flat surface. The first semester or so is, and then you get into 3 dimensions where you're trying to picture like taking an irregular shape and then rotating it around so it's creating a volume, right? It's an irregular shape in the plane and then it gets rotated around to make a volume. You got to be able to picture that. And that becomes particularly hard for people to picture. Now I think this is where not yet. So in 2 dimensions in the plane, we have quadrants, right? Because those 2 lines on a flat surface break us up into 1, 2, 3, 4, right? But in 3 dimensions, we don't just have 4 sections to space. How many do we have? You have 8, and they're called octants, right? So you have 8 octants. Now this is my pride and joy here. You got to watch it, okay? Okay. So give it a second. Okay. We'll get it. We'll get it. Oh, but that was the presentation. So maybe this is that's the slideshow. Okay. Okay, so here's the three axes again, right? X and Y and Z. It's positive, positive, positive. And if you try to imagine, I mean, these cubes actually go on forever in each direction. The naming convention for the quadrants is, right, the first quadrant is when all three are positive, or the first octant is when all three are positive. And then just like it is in quadrants, you go counterclockwise around. This time you're going counterclockwise around the z-axis. So that's 1, that's 2, that's 3, that's 4. Okay, now to go to the 5, 6, 7, and 8, you just drop right down below 1, 2, 3, and 4. So 5 is going to be here. 6 is going to be here. 7 is where? In the back left. Watch. There it is. There it is. Okay. And there's 8. Okay, watch this again. We're not done yet. 1. 1, 2. See how I got the letter? It's at a slant like that. 3, 4, 5, 6. Uh-oh, where's 7? Where's 7? There it is. 8. Okay, one more time. 1, 2, 3, 4. If you didn't already get it, 1, 2, 3, 4, 5, 6, 7, 8. Get it? Okay, watch it. Hey, a student asked for it. Actually, I think Pierce, you probably saw it last year, right?
Yeah, that was right after.
I think I had him exploding or something at that point.
So
Yeah.
I really thought you were going to say
Well, I'm not that good with PowerPoint anymore. But when they first came out with PowerPoint, and I was in the Air Force, I was like, for my organization, which was a big organization, I was the command briefer, right? And up to that point, the command briefing was on little slides. You know, you have a carousel and you put slides in. If you watch Mad Men, that was a big part of Mad Men, right? Well, that's how we did it. But at that time, they wanted to get everything into PowerPoint. So we were, having to get all those pictures put into digital files so that we could put them into PowerPoint. And the files were huge. It was like, I don't remember how many slides. There's a ton of slides. And, in those days, memory was really an issue. Storage space was really an issue. I mean, it's a really big deal. In those days, I was a PowerPoint ranger. That's what we used to call it. But these days, I barely get along. Mason, are you catching all this? Yeah, I got it. Okay. No more. That's it. Okay. Yeah, I know. I don't know why it changed, or I don't remember changing it, but. I'll try to fix it. Okay, so now. I don't remember if I made it last year or the year before. But so now we move to section 11.2. Now that we have some concept of three-dimensional space, right? Now we're going to do everything we did with vectors in 2 dimensions. In this section, we do in 3 dimensions. Nothing is really added. The next section, we actually do something that only makes sense in 3 dimensions. But everything in this could have been done in 2, could have been done in 3. So now we have vectors that have 3 components, right? V1, V2, V3. So the V3 is added. Where am I at? And again, you could have that written in component form, or you could have it as a linear combination of the standard unit vectors. Just that now the standard unit vectors are I is 1, 0, 0. Right? J is 0, 1, 0. K, which is the third one, is 0, 0, 1. Okay. We're good. Okay. Slow me down if I go too fast. So here's all the things we'll do with vectors in space. The first statement, that two vectors are equal only if all their corresponding components are equal. The magnitude is calculated by, and it should look pretty similar, right? Now it's, if you cover up the U3, right, that looks like our magnitude formula before. But now because we got a third component, you got to add U3. I mean, in fact, the part of the 11-1 that I skipped was using a distance formula in 3 dimensions, and that's more or less a distance formula in 3 dimensions. Okay, we still find a unit vector by dividing a vector by its own magnitude. A unit vector in the same direction is found by dividing a vector by its magnitude. Right? We still add vectors by adding their components. Now we just have to add a third component. We do scalar multiplication, right? Multiply by a constant. It just means multiply every component by that. And we can do a dot product, right? Again, if you cover up the last piece, that looks like the dot product we already did. But now we've got to add plus U3, V3. So everything will work exactly the same. Just got one more term. You okay? Tutti sono bene? So let's see. Let's find a component form of a vector given an initial point and a terminal point. How do you find component form of a vector? You subtract terminal minus initial, right? Terminal point minus initial point. Okay, so the terminal point is 3, 6, 4. The initial point is 3, 4, 2. Right. So the component form of a vector, remember, it's going to be in the angle brackets now, not parentheses. 3 minus 3. 6 minus 4. 4 minus 2. Right, which is 0, 2, 2. Okay, said find the magnitude. Right, how do we find the magnitude of V? Okay, so it's the square root of, no, 0 squared plus 2 squared plus 2 squared, right, which is the square root of 8. Okay, that's the magnitude, right? Then find a unit vector in the same direction as vector V. How do you do that? You divide the vector by its magnitude, right? So that would be 0 divided by the square root of 8, comma, 2 divided by the square root of 8, divided by 2 divided by the square root of 8. Because that could be simplified. The 0 over the square root of 8 is 0. Actually, the square root of 8 is 2 times the square root of 2. So that would be 1 over root 2, 1 over root 2. And I guess you could rationalize those two. I mean, these are all pretty much the same processes that we already used in 2 dimensions. Good. Right, find the dot product of 2 vectors. 2 vectors in space. Right, how will we find the dot product? Right? Right, it's going to be 0 times 4 plus 3 times negative 2 plus negative 2 times 3. 0 minus 6 minus 6, negative 12. Right, so just like when we did it in 2 dimensions, if you take the dot product, the result is a scalar, right? It's not another vector, it's a scalar. Good. Okay, the angle between 2 vectors, same formula, right? Same formula. But now the dot product and magnitude, we know how to do them. Same, they work the same. The formula is the same. So let's do the dot product first. U dotted with V in this case is 1 times 2 plus negative 2 times negative 3 plus 4 times negative 1, which is 4. The magnitude of U. How do I do that? 1 squared plus negative 2 squared plus 4 squared, which is what, 16 plus 4, 21? How about the magnitude of V? Two squared plus negative 3 squared plus negative 1 squared, which is 4 plus 9, 13 plus 1, 14. Right, and that's all we need to plug in. So we do that. Right, cosine of theta equals 4 divided by the square root of 21, square root of 14. And I'm going to do that on the calculator. Okay, so that is 4 divided by second square root. Now I'm just going to put all inside the 1 square root because that's the way radicals work. 21 times 14. There, I don't even need any more parentheses or anything. 0.2333. Okay, once you've got the cosine of theta is 0.2333, then you find the angle by doing, no, cosine inverse. Second cosine for the cosine inverse. Second answer, which is above the negative sign, 76.5. Okay, so 0.23. So let me write this down. 0.2332. The cosine of theta equals 0.23. 2, 3, 3, 3. Theta equals 76.5. Okay. Right, so most of the stuff should seem pretty easy. I mean, most of you didn't have much trouble with this whole section on dot products and things like that in 2 dimensions, and this is just more of the same. Okay, now I talked about last time the idea of 2 vectors being parallel. They do have that in this section. When it comes into space, they do talk about how is it that 2 vectors would be considered to be parallel. And they are parallel if they're scalar multiples of each other, right? You could just multiply times a constant and get the other vector. This is kind of a weird example, the way they've asked it. You know, I think the homework problems say, here's 2 vectors. Are they orthogonal? What does orthogonal mean again? Yeah, more perpendicular, meet at 90 degrees. 2 vectors are orthogonal, right? What's the check for that? What is the check to see whether 2 vectors are orthogonal? Dot product is 0. Remember, if the dot product is 0, they meet at 90 degrees. Okay, now we've got to check for, are they parallel? So I think the homework questions are like that. Are they orthogonal? Are they parallel? Or neither? But this is a little different. It says vector W has an initial point and a terminal point. Which one of these 2 is parallel? Meaning it is a multiple of the vector W. So first we've got to find the vector W. Again, how do you find the vector component form if you know the initial point and the terminal point? You use the theory of relativity and square it and what? Come on, you subtract, right? So W equals terminal minus initial. 3 minus 1, 2. 2 minus negative 2, 4. 1 minus 0, 1. So the question is, which one of these 2 is a multiple, is a scalar multiple of that? A. Okay, what would you multiply times W to get this 2? So either you're multiplying this one times 2 or this one times a half. Either way, these are scalar multiples of each other. So these scalar multiples. That's not even a... Okay. Remember, what were the hardest problems that we did when it came to the 2-dimensional vectors? The balance of forces stuff, right? Okay, well, we're going to do one like that. And it takes up the rest of the slides. But actually, I've just kind of cut and pasted from the book. Because I wasn't happy with the way the one I did the other day came out. It was just like, I've explained it better in the past. So I'm trying to do better. So you could have, we can have a balance of forces in 3 directions, which is highly likely that you would have to do that. So this one, this example 7 in the book, it says you've got a weight, here's the weight, of 480 pounds, and it's being supported by 3 ropes. So you're having to try to picture this in 3 dimensions. I mean, it's the book's graphic, so it should be better than I could have drawn, right? There's one rope that's pulling. Actually, they've labeled this as a point S in the middle, right above the weight. And so you've got one rope that's pulling up to this point, P. You have one rope that's pulling to this point, Q. And you got one that's pulling to this point, R. So they're pulling in 3 different directions. And, you know, it's hard to see from the picture, but we assume they're not regularly spaced. So we're going to have to calculate. We want to know what's the tension in the 3 ropes. What's that? Oh, no. It's 3D. I mean, you're in space now. So there's going to be components of all 3 of these vectors that are going in the x direction, in the y direction, and in the z direction. You're going to have to make a balance of all of them. I mean, how many unknowns are there if we've got to find the tension in each rope, and there's 3 ropes? So how many equations do we need? 3, right? And so you've got them because you've got 3 components in space. That's what we have to do. You guys done? Okay. So the thing to keep in mind here is that we're going to have to make a balance of the forces that are pulling here. We've got these 3 that are pulling up and in 3 different directions, horizontally, let's say, and then this one which is pulling straight down. So we're going to have vectors to represent them. Now the easy one is the W. The W is pulling straight down. So that's 0, 0, negative 480, right? Because that's the negative direction pulling down. These 3 vectors, this is kind of like, remember, you can write any vector as the magnitude of the vector times a unit vector in the same direction. I mean, we don't have, like we did in the homework, the direction angle where you can just say cosine theta, sine theta. We can't do that anymore. But what we can do is get the component form of the unit vector in the same direction as u. And, this is the directed line segment SP, so it starts here and it goes there. And this is SQ, so it starts here, it goes here. This is SR, and it starts here and goes there. So how are we going to find the vectors that go from S to P and S to Q and S to R? Those are initial and terminal points. Subtract, right? In every case, you're going to subtract. And that will look like, again, this is all in the book if you wanted to look there. So here's where we're doing the magnitude times the unit vector. So we have to do the magnitude or the vector by subtracting the terminal minus the initial points. That's what all these subtractions are right here. Okay. And the magnitude is still just carried along. Nothing's changing there. Now, what does the 3 represent right there? Yeah, I mean, that doesn't even seem right. Oh, it is, sorry. So this component form of the vector, I'll just write it here. 2, comma, negative 2, comma, 1. Right, that's what this math is right there. So when you find the magnitude of that, it'll be the square root of 2 squared plus negative 2 squared plus 1. 4 plus 4 plus 1 is 9. The square root of 9 is 3. So this is the magnitude. So that's where this comes. This now is a unit vector pulling in the same direction as u. So u equals the magnitude of u times the unit vector pulling in the same direction. Right? The same thing being done here, right? This is 0. 4 minus 2 is 2. 0 minus negative 1 is 1. Right? The magnitude would be the square root of 0 squared plus 2 squared plus 1 squared, which is square root of 5. That's where that comes from. And the last one, this is negative 2, and positive 1. The square root of negative 2 squared plus negative 2 squared plus 1 is 3. That's where this comes from. So now we've got 3 vectors, u, v, and z, that are pulling in some direction up. And then you've got the w, which is pulling down. And you know that the sum of all 4 equals 0 because the thing is stuck in place. It's not moving anywhere. It's just stuck. And if you move the w to the other side, but w is the one vector that we actually know, right? We don't know these 3 yet because we don't know the magnitude of u, v, and z. On this one, we know the whole thing. That is the vector w. So here they've moved the negative w, or subtracted w to the other side. So u plus v plus z equals negative w. So that's what we need to use to set up something that we can solve for these three. Right, so this is copied from the last page, all this stuff here, right? Okay, now if I make a system of equations, it's going to look like this, right? It's 2/3 times the magnitude of u, plus 0 times the magnitude of v, plus negative 2/3 times the magnitude of z has to equal 0, right? It's the x components of the vectors all have to be the same, right? So that's where this comes from right here. Right. For the second component, the v2, let's say, it's this u times negative 2/3, magnitude of b times that, magnitude of z times that has to equal 0. That's this right here. And the last one will be 1/3 times that, 1/5, 1 over the square root of 5 times that, 1/3 times that equals negative 480. That is that. Now, at that point, you have your options. How do you solve a 3x3 system of equations? And honestly, matrix, right? I don't think anybody wants to be messing with Gaussian elimination or substitution, back substitution, all kinds of stuff. Could you? Yeah, but it would have been a mess. Instead, just turn it into a matrix equation, right? There's the 2/3, 0, negative 2/3. That's this. Negative 2/3, 2 over the square root of 5, negative 2/3. 1/3, 1 over the square root of 5, 1/3. Right? The variable matrix are the three magnitudes, which is what we're being asked to find, right? The magnitude of u, the magnitude of v, the magnitude of w. And the B matrix on the other side is 0, 0, 480. So again, how do you solve? We did it in the homework. How do you solve the matrix equation? If A times X equals B, then X equals A to the minus 1B, right? So you can enter all that in. It's a 3x3 matrix. They didn't show their work from here to their answer. They just showed the answer. We good, Taylor? Okay. So you do your X equals A to the minus 1B, and these are the solutions. So the tension in each rope, this is in the U, this is the V, and this is the Z. Okay. And that's it. I mean, except for that last one, most of that wasn't too hard. Now, the homework problems include from the first section, right? It's just, you're given some things to say, like X is greater than 0, Y is less than 0, Z is greater than 0. Which octant are you in? Right? That's what all those questions are right there. Identify the octants based on what you saw in that wonderful PowerPoint, right? And then the rest of them, it's a lot of problems, but most of them are pretty basic. Things that you didn't find you have any trouble with in 2 dimensions, and now you're doing them in 3 dimensions. And of course, there's one bonus question right here for all you engineers. Okay? All you AAA Academy future architects and engineers of America, whatever that stands for. Okay.